Bismillahirrahmanirrahim. Assalamu alaikum. Recall, in the previous session we have already seen what is an analytic function. So we have seen when an f is analytic function, right? And we have also seen what are simply and multiply connected domain. So these are some of the assumptions that we need to proceed ahead in this session, right? Okay. So in this session, we are going to move towards defining one of the very famous theorem in the complex analysis. So it's not basically Cauchy Goursat, but it's only Cauchy's theorem. So first I will define Cauchy's theorem. We will of course define and prove Cauchy's theorem, right? So Cauchy's theorem, it was given in 1825 by uh, French mathematician Louis Augustin Cauchy, who proved following. So let me state the theorem. Suppose that a function uh, f is analytic. Analytic means differentiable at a point z, let's say z naught, and we can find a neighborhood over that z naught such that f is differentiable on that as well. So suppose we have a function f which is analytic in a simply connected domain. So far our discussion is relying on simply connected domains. Simply connected domain. So suppose we have a function f which is analytic in a simply connected domain. Let me call that domain D. So and that, and additionally the derivative of f is continuous. So it's derivative in the sense of complex differentiation. So its derivative is continuous in D, means in domain. Then for every simple closed contour C in D, so inside the domain we have this. So we have what? We have this following. So we have this contour integral over C of the function f of z with respect to z is 0. So what we are saying basically, that suppose we have got a domain, let's say we have got a domain D, and we have f, a function which is analytic over this domain. In other words, you can take any point. So function is differentiable at that point, and we can also find a neighborhood over this such that f of z is also differentiable on that neighborhood. So suppose we have a function, we have a domain. Additionally, this function is analytic as well as its derivative is continuous on this domain. Now, if you take any C, simple closed contour, any C that you like, so there can be multiple closed contours inside this domain. So if you take any C which is simple closed contour and you find out this integral, it turns out that integral is going to be 0, right? So this is the statement of the Cauchy theorem. Now we will move towards proving this theorem, right? Before I prove, I will state some of the terminology. Let's prove. So we are given with a function f of z. Since f is complex valued, so I can write this f. So like I will be using u plus iota v for this f of z, uh, to be precise or to make things look easier. For differential of z, I will be writing differential of x plus iota times differential. So like delta x plus iota delta y. So it is delta of z, and I will be using lim for this uh, limit partition P approaching to 0. So I will be using this, and for some uh, k equal to 1 to n, let's say I will be using this. So for f of z, I will use this. For change in z, I will use this. And for this limit with partition, I will use this term. And for this summation, I will use this. So now, if I recall the definition of integral in terms of summation, so it turns out that it is given by the integral over c of f of z dz is equal to limit summation, so f of z change in z, or I can write limit summation f of z will be replaced by u plus iv, and this guy delta z will be replaced by delta x plus iota delta y. So now you can perform, these complex multiplication operation, and it turns out that it is given by, so you can multiply this u times change in x plus iota times u change in y plus iota times change in x v and minus v change in y. Okay, so this is right over here. So now we can also separate the real and imaginary parts. So then we will have limit summation with this, real part, and limit with this imaginary part. Let me take iota here. So it's change in yu plus, so v change in x, something like that, right? But the interpretation of this line, this over here, when we turn back into integration, integral, it turns out that we can write this as integral over c of this u dx minus v dy plus iota times integral of u dy plus uh, v dx, right? V dx. So this integral over this contour can be given by this. So why have I made all this effort is because I'm going to use this when I will be proving the Cauchy theorem, right? Now we will prove this, we will prove now the Cauchy's theorem, where we have to show that this integral over contour of this analytic function in the simply connected domain is 0. So as we have seen that the integral over any curve uh, is given by integral of u xy with respect to the x minus v xy with respect to dy plus iota times integral over this closed curve of v of xy dx plus u of xy dy. So what I have used over here is this above one, this result. So I'm using this result that we have recently seen. So you can see these u and v are basically functions of x and y. U is also function of x and y, v is also function of x and y, right? So we are using that, right? So what can we do next is we can apply the Green's theorem, because you can check that we are already in the assumptions of Green's theorem. Uh, you can relate it with your multivariable calculus. If not, then we will also make a video on this Green's theorem. So like this quantity with the help of Green's theorem can be written in this form. So the integral over the region inside that contour of minus uh, partial derivative of v with respect to x minus partial derivative of u with respect to y and dA plus iota times integral of partial derivative of u with respect to x minus partial derivative of v with respect to y over that region with respect to dA is given by this. Now, since f is analytic, since f is analytic, so since f is analytic in D, so we can also check back that u and v should satisfy this following is coming out of the complex differentiation, which we will be covering in the next coming days. So u and v should satisfy Cauchy-Riemann equations. So what are the Cauchy-Riemann equations? So Cauchy-Riemann equation says that partial derivative of u with x is partial derivative of v with y, and partial derivative of u with y is same as partial derivative minus times partial derivative of v with respect to x. So because these two are equal, so you can say that this goes to 0, and because partial derivative of u with respect to x is same as partial derivative of v with y, so this goes to 0, and hence you can say that this integral over this simple closed contour of this analytic function over the simply connected D is 0. So this was Cauchy's theorem. Next, we will see the Cauchy Goursat theorem.